Okay, so let's keep going. So infinite potential game is basically say looking at the continuous case, right? This core knot it could be considered as an infinite potential game. And then in this case that you, instead of doing this ordinal or this exact set of a sort of a definition of the potential function and relationship with reward, you can actually define from this fourth order relations that can define that. Okay, next we move to this network congestion game. The reason we introduce this is because this is one of these popular potential games, right? Or one of the well-known potential games. So consider that you got this direct graph that with V and E, right? E is H and V is basically the nodes. Now each H, E in this H of the nodes has a delay function Fe. Okay, so think about this as sort of like a transportation graph. Then this function in one of these H indicate a road, and this F function indicates how much time you can actually travel from this finish travel in this road. Then the strategy of user I is basically whether they're going to decide to choosing that path to reach to their destination from source. So the source is Si and destination is Ti. So the delay of the path is basically the sum of the delays of H on the mass. So what this means is that when you have a path from source to destination, and then you basically summation all this time you spend in each of the path, in each of the H, in other words, each of the road, and then become the total time spent, in other words, total time delays that from that path. And the user basically want to minimize his own delays by choosing the best path, right? You don't want to go to the destination in one of these most jammed sort of roads, right? You rather to pick up the road which has less vehicles. So this delay function is actually depends on not just yourself, but also on the other users or drivers who are in that road. So that means that if you have a more number of people using that road, that means these delays would be larger, would be bigger. So here's an example. Say you got these 3 vehicles and 2 destinations, and this is sort of a traffic. So the H is basically the arrows between each of the nodes, and the function indicated here, for example, 6x6 power 6 plus 2x is that x is the number of users who choosing this path. Or choosing this H. If the 2 people, then it would sort of obviously the X is the number of people. Then you have more people, then there will be a higher delay that you would have. And based on this, then each of these vehicles, let's say starting from S1, S2, S3, they would try to coordinate this, right? Try to coordinate, make sure that globally this traffic network is more efficient, but also for themselves, they would be able to sort of optimal in terms of this shortest path that they could come up with. So you could do this, or you can actually travel from here, right? It depends on the the traffic. So just looking at this simple traffic routing, and suppose you they have 100 drivers starting from town A, want to go to town B, and they have 2 options. One is from here, it would spend 1 hour for sure, or if to go from the this route, and in this route, then the delay would depend on how many cars, how many drivers in that. For example, if hundreds of drivers go down, then would spend sort of a 1 hour. So in this case, then what is the traffic on the network? And obviously, everybody gonna go to this road, right? Because then it will be break even in terms of delays. If any number is smaller than that in terms of drivers, for example, if I have 99, 1, and this guy would obviously want to deviate from that choice because it's 1 hour here is smaller than 1 hour, so they'll actually go back to here. So in the equilibrium, then you will always have this unbalanced traffic pattern. So as I said, that if you're 50-50, then your total delay would be 0.75 hours. Right? So for example, you got 50 people here, 50 drivers here, then the total delay is 0. But it's interestingly, in the Nash equilibrium, it's not the best, right? In Nash equilibrium, it's basically the average delay is 1 hour. Okay, so this is really shows that in fact Nash equilibrium not sort of a sometimes not really consistent with the sort of a socially optimal solutions. Okay, let's look at another example. Is that we got a slightly more complicated case. We have additional nodes in between, and we still have 100 drivers. And you can see that if you do that, this Nash equilibrium is basically 50 up, 50 down. Then you can calculate this sort of a delay is 1.5 hours across, average across the drivers. But then, some of the guys say, okay, in order to improve the traffic, can we build a faster tunnel, right? Faster highway between these two nodes with no delay whatsoever. And then you can think about this. In this case, what would be the Nash equilibrium? Okay. So you can find that people doing this. This is your path of these 100 drivers in this case. And you can actually calculate the delay. Okay, so in this case, adding this fast road really doesn't really help. Adding the fast road doesn't really help. So this is sort of one of the paradox that being heavily studied in the literature. And so what I try to say is that this Nash equilibrium, it's probably a crucial role on all these things because each of the drivers they optimize their own sort of objective independently, and therefore you also have one sort of common social measurement. But this because it's selfishness of this individual drivers, then it's not necessary to be sort of consistent on that. Therefore, it's very interesting to need to do some analysis. So formally, this congestion can be formulated as follows. It's really a very sort of popular coordination, right? Try to resource allocate in a much more, not coordinate, sorry. So resource allocation problem is very interesting because this resource allocation not in the globally, but individual players, they try to sort of optimize their own objective in order to choosing what kind of resource they're gonna consume. So mathematically, you can define this as I number of players, n is a set of resources, like for example the ages, the roads, and the s is their decision. In other words, for all the i's, and then each of them, SI, is the set of resources they are using, right? It's not necessarily going to using all the, the roads towards the destination. You're going to obviously select some of the, ages or the roads. So this is basically your strategy. And then you've got this cost or the benefit, let's say the benefit that we try to maximize, is that this based on the resources you're using, and then you would have in the end the benefit of using that resources. For example, in the traffic, it could be this sort of a negative of the delayed hours. But how exactly is this utility going to calculate? Is really, again, based on the strategies, joint strategy, right, for all the drivers, all the players. And this is sort of summation of this thing about is the delays or the negative of the delays across all the resources this I user has been chosen, right? Then you basically say, okay, given this J, is a J resources I'm gonna choosing. But it also this J also depend on the K. K is this the number of drivers, number of users who are consuming these resources, together. For example, this is basically it would be like this C would be the function that we specified here, right? And also it depends on the X is the number of people who's using that resources. Okay, so this is a sort of a simple mathematical definition of that. I just want to quickly go through is one of these widely used theory, well-known theory, is that every congestion game is a potential game, therefore has a pure strategy Nash equilibrium. So give this congestion game as quite nice property, right? If you define this as this, define this game as we define here, has that kind of reward structure, okay, then you would always guarantee that it's a potential game, therefore you always getting there's a pure strategy Nash equilibrium. So how can we prove that? This is very simple. I'm going to very quickly go through that. Just highlight how you can actually prove that. So if you want to prove this congestion game is a potential game, obviously you want to prove that you create this phi function, right? And basically show the difference of this phi respect to this player I, okay, their strategy change would be same of this player I's payoff change when they change the same sort of strategy from Si to S prime. So that's basically how you can prove. So you before to do that, this proof is basically give this need to have introduced additional introduction notation. This notation is that so instead of have this K, J, remember this number of users who are using this resources J. Using this K, J, I is that is basically say if I have this resources J, and I is using it, but then I have this count is not just counting. I will remove this I, I won't count this I, but I will count the rest of these users. So this basically this means. So the I here, sorry, this is an indication function. It's just a count, right? Whether the J is the resources that are being used by I prime, but this I prime is not in I. So basically it's just a Kij equal to Kj minus 1. Okay, if the I is using resource J, I think that's basically this means. So then you can actually write it down this utility difference if you use S prime, move from S prime Si to Si prime. So this Si prime is a set of, remember, this is a set of resources that this user driver I is using, right? Si prime is I have alternative set of resources gonna using to achieve my goal. I want to see the difference between this utility. I think this is basically the calculation is, right? And this is basically say equal to K. but just for the later that needed. So instead of doing this k, I'm going to doing this, kji plus 1. Okay, so then we can define a utility. Sorry, we can define a phi function, a potential function, as the following. So again, I mean, it's different with the one that we show is a product, but instead of this, we basically enumerate all possible J resources being consumed by I's, right? This is basically, remember, this I is a set of users, and then you sum it all together, and this is basically K is accumulated from 0 to Kj. And I don't know how did it derive this, but you can just want to say, suppose you have this function, you can show this actually is a potential function. And then you could write it down this into this two part. One is that you have these resources that from all these other users, and also resources being used by this user I, can then basically split this into two. Okay, once it's split into two, and when you do this, adding this Si prime into it, you can actually say this actually same, and then this is basically this two minus this two is really equivalent to this utility that we just defined, and therefore prove that the fact that congested gain is indeed a potential gain. And then they have this all the nice property of the potential gain. For example, they always have guarantee you have a pure strategy Nash equilibrium. Okay, so that's proof. So do a pure, let's maybe just in case there are questions. Do we have any question? So the here is that do we have a pure strategy Nash equilibrium in traffic routing games, right? And the answer is yes, right? Because that you have this potential game kind of a intuition, right? You have this say every traffic routing game, right? You always it's been proved it always is a potential game. You always find a potential function. You can define this, right? You can always define the potential function like this, and therefore you can actually show indeed it is a potential game. So because in potential game, a pure strategy is always exist. Therefore, you can always say that there's a pure strategy Nash equilibrium, and so in the congested gain, any iterative best response process will terminate and eventually convert to PSAE. Pure strategy Nash equilibrium. So this is also another follow-up equilibrium theorem, and is sort of say, okay, if I always do best response, I have a best response process. Remember, when we're talking about Korno's duopoly game, that we have this best response process, right? Each time we do best response. And so equally here is that you can also do this best response. So here is like best response loop. And you can always guarantee you to converge to these either global or local sort of maximum point of the potential function. Therefore, here would give you a pure strategy equilibrium. Okay, so that's it for the potential game lecture.